Okay, our session is being recorded. This is week 4 of Data 640, and now we're going to start into some of the heavy lifting, so to speak. Hopefully you now have a much better understanding. Probably not perfect, because certainly there's plenty to learn, but a better understanding of some of the transformations, some of the imputing methods, some of the things you got to do. And now when we start putting those things to work, you will see their actual utility. Okay, so we're going to focus again in this course on the big three techniques for building predictive models: decision trees, regression, and neural networks. We're also going to cover ensembles, a little bit on text mining, and so forth. And we're starting that with this 2-week session on decision trees. Now, the way I do it is a lesson, which will be tonight, on how it works, and then a lesson next week on how SAS does it. So we'll be going through some examples. In the meantime, of course, you can be planning your assignment, maybe even working on it if you feel comfortable with decision trees already. The main thing is to find a good data set. And again, you don't have to use just the ones that are available to you in our course content. I've provided some links where you can go and get other data sets. And part of the assignment is, of course, to employ or to use a robust data set. And by robust, we mean lots of cases, lots of possible variables to use as the inputs or the features. So that's part of the problem. All right, well, let's talk about decision trees. By the way, before I get too far along, I'm going to post a couple of links probably in the announcements sometime in the next week or maybe even tonight about a couple of really good articles that I would have used last week had I been aware of them. One is, there's a guy, we've talked about some pretty big names in this business. Nesbitt, one of your authors; Elder, one of your authors; Abbott, one of the people I really rely on a lot. There are many others, but this guy, B-O-I-R-E, Boire, is also in that pantheon of heroes, so to speak. And I've got a couple of articles from him that are pretty insightful and easy to read and very useful, so I'll post those. Okay, here's our agenda. Slide or two on background, then we'll get into how does a decision tree actually do its thing. And basically, we talk about the methodology. I think we all have a conceptual grasp, and we've seen decision trees either in 610 or elsewhere. So we know a little bit about, I see, it splits the data into chunks and so forth, but we need to know exactly how you do that. Okay, and then we'll talk about advantages and weaknesses, and finally, the usual stuff to finish up. Okay, background. Just a reminder, we start with decision trees for a lot of reasons. It comes early in the textbook, in the SARMA book. That's one reason. That's not the reason I like to go with it first. I like to go with it first because it's certainly, A, the most popular technique, and B, it has many other advantages, such as easy to understand and explain. Unlike regression, unlike neural networks, which require a little when you're trying to explain those, this is easy to understand. If we ask somebody this question and they say, I make more than this or less than this, you go here. If you make more than that. And so basically we end up with rules as our output. And rules are rather easy to grasp. If the barometer's dropping and there's a lot of clouds and the weather channel says it's going to rain, then take an umbrella. Similar, except we don't build the rules by hand like you would in building an expert system. We build the rules with machine learning tools, in this case, SAS Enterprise Miner. They're easy to build. You'll be able to build these trees very quickly once you have your data set brought in and stuff. You hit go, and basically you're there. There's a few tweaks you can do, and we'll talk about that next week. All the settings, or at least many of the settings that are available to you in Enterprise Miner. But basically, it's very easy to build trees. And they have a lot. The reason they're so easy to build is, first of all, look at these nice features. No problem with missing values. We talked last week about how important it was to do something with missing values. Eliminate the cases, eliminate the variables, impute values in one of many ways, because regression and neural nets can't deal with those. Or they can deal with them, but it skews the results quite a bit. Well, decision tree, not a problem. Can have nominal and continuous inputs, okay? So we don't have to convert things like we do, again, sometimes with regression and neural nets. We'll talk more about that when we get to those, but they like to have a certain kind of inputs. They can't handle all kinds, whereas decision tree says, not a problem. Scales well for large problems. What do we mean by large problems? Well, again, you could have millions of rows or cases. You could have hundreds or thousands of inputs, possible inputs, because what happens is it picks the inputs automatically using a process we're going to outline in just a minute. And that's one of the real values. And again, it's the most popular technique. Surveys show anywhere from 65 to 75% of organizations doing any kind of predictive modeling, their first choice is decision trees. And of course, it can be used for either classification problems or prediction problems. So we can handle categorical variables or continuous variables. We call it regression trees, but they're trees. We'll talk about that. So with all these positives, you might be wondering, why are we even studying the other techniques? Well, there's one that's not on this chart. It is not usually the most accurate technique in terms of accuracy. So yeah, it's easy to do things, but oftentimes, can't say always, oftentimes regression models and or neural network models will outperform them in terms of the accuracy measures that we discussed briefly last week. Nonetheless, decision trees are extremely powerful and often give very good answers and should be certainly in the toolbox. Here's a chart from TDWI. Remember, a big fan of the Data Warehouse Institute stuff, a survey in 2014, so not that long ago, showing the percent using different techniques. And you can see a large majority using decision trees. You get down here to ensembles, that's just starting. We'll say something about that in week 11 or 10. When you get into neural nets, not even 20%, okay? So of the main predictive models, there's decision trees, there's linear regression for continuous variables, there's logistic regression for categorical variables, and there's neural nets can do either. So, and of course, decision trees can do either. So, you know, this is a biggie, okay, in terms of that. Okay. Now, what exactly does a decision tree do? Well, as you know from seeing, and we're going to go through an example or two, you basically start out with a big blob of data, and you'd like to, let's stick with the classification approach. You'd like to classify that into people that are green and people that are over 50 or something like that. You'd like to classify the pot of inputs, cases, maybe into people who will buy the product, people who won't buy, people who are likely to churn, people who aren't likely to churn, fraudulent transactions, non-fraudulent transactions. And by the way, it doesn't have to be binary. We always use binary examples because they're so much easier to grasp and understanding, but there can be multiple categorical outputs. It doesn't have to be just two categories. Okay? So what the decision tree does is find a variable, one of the predictor variables, and a place in that predictor variable, if it's continuous, because it might be, you know, numbers, that best divides this mixed group of outputs, some who churn, some who didn't, into more homogeneous groups. In other words, there's more, once we do the division on a particular input or predictor variable, we now have two pots, and in one pot there will be more of type 1 output, and the other pot there'll be more of type 2 output. And then it does it again, and again, and again, and again. So it's a recursive algorithm, meaning once you've done it, that's all there is to it. You just do it again, except now you do it on the smaller pots that you have. And so you end up with, well, you could end up with lots of pots. But each time you split, which is what we call that separation, you are finding a way to more homogenize the answers. In other words, you're putting people more, or you're putting outputs. I say people, it's really outputs. Churners are becoming more and more in one group, non-churners more and more in a different group because of the variables. The ultimate result, of course, is some rules. If you didn't answer your phone, and if you haven't paid your bill, and if you're this, and if you're that, then you're 98% likely to churn. And then we can take some action to do something about that. So the real niceties here are quite widespread. And of course, once we have these logical rules, as some of you, all of you who took Data 610 saw, we can turn those into immediately implementable code rules that we can put right into whatever system we have. In fact, we used Big ML you notice there were like 15 different ways to output the rules so that you can incorporate that directly into whatever coding scheme your organization uses. And of course, that automates decisions. Remember, we're focusing on a lot of things here, but one of the things that keeps slipping through the cracks sometimes in the real world is just building the model is not the be-all and end-all. You have to implement the results, especially if they're good. If you say, wow, this is a good model, it really does identify churners from non-churners. It identifies fraudulent from non-fraudulent, people who are likely to buy versus not likely to buy, people who are likely to contribute versus not likely to. You want to automate that if you can, because remember, we're dealing with repeatable decisions. We're dealing with things that happen at the operational level, not the strategic level, where things are more unique. Okay, so now how do we do this? All right, let's say we have a data set with 500 people who paid back a loan and 500 people who didn't. And we have various features, inputs, remember, selection variables about them. How much they make, how long they've been with us, how big their loan was, whatever the key things are. We don't need to worry about that yet. So we start out with a data set that's 50-50. So if you were to pluck one of those people and make a guess as to whether they pay the loan back or not, your odds would be 50-50 being right. That's not very good, is it? So let's say we find a variable that can split that tree. So we start by looking for a variable, a feature, one of those inputs, from the data set, and a value for that feature. So it's not just a feature, but a value for the feature that will best separate the yes customers from the no customers. Okay? And we split on that feature. So what do we have to find? We have to find a variable and a feature and a value of that variable. Because if it's numerical, there can be lots of values. Suppose we want to split on how much they borrowed. They might have borrowed $50, $100, $75, $10,000, $500. Where do we split? We'll talk about that in a minute. But what happens when we find that feature that is the best feature to split on, and the value of that feature that is the best value to split on, we split. And so now we get something. Now I've got a question mark here because I'm not showing you what the feature is. We'll get an example that has more specificity to it in a minute. But this is just conceptual right now. We've split on something. Now, if you happen to find a feature, maybe it's hat size or something. Everybody whose hat size is greater than 7 paid the loan back. Everybody whose hat size is less than 7 did not. Guess what? You're done because you have a fully, excuse me, I'm fighting a summer cold. I get these every year. You have found a feature. Again, we don't know what it is because I'm not selling you. This is not a real case. But we have found a feature that has completely separated our mixed data set into two homogeneous sets. All of these characters paid the loan back. All of these characters did not. So, wow, that's done. Now, is that ever going to happen? No. It could happen for a trivial problem, but in the real world, of course not. You're not going to find one feature, one value of one feature that splits your mixed group into perfect homogeneous subsets. If you do, the problem was trivial and they didn't need you to do it anyway. More likely is the best split, let's say. Remember, it's the best value of the best variable. That first split did this. Instead of having 500 yeses and 500 nos, if your hat size is greater than 7, 275 of those people paid back the loan. 180 did not. If your hat size is well, actually, this would be less than 7. This would be greater than 7. 320 did not pay it back. 225 did. So you can see the odds if your hat size, let's say this is the greater than 7, size 7. If your hat size is greater than 7, the odds of paying it back are less than 50-50. If your hat size is less than 7, the odds of paying a loan back is more than 50-50. So we've taken a step towards homogeneity, haven't we? We've taken one step with one feature, and we said, you know, this is better than 50-50. So if I pluck one out of this group and had to guess, are they going to pay the loan back or not, I would say yes. If your hat size is less than 7, you're going to pay the loan back, and I would be more than 50% certain of that. On the other hand, if your hat size is greater than 7, I would say no, and I would be more than certain that answer is right, as opposed to when I started. So now what do? You split again on the next best feature, the best value of the next best feature. Okay? And again, we don't know what that is because it's not a real problem. And let's say our 275 yes and 180 no's, when we split on that feature, maybe that's how much they borrowed. If they borrowed less than $100, a bunch of them paid it back, a few of them didn't. If they borrowed more than $100, not very many paid it back, most of them didn't. On the other hand, if their hat size was greater than 7, and we're here, now this doesn't have to be the same feature, by the way, but let's assume it is. They borrowed less than $100, most of them paid it back. They borrowed more than $100, most of them did not pay it back. Now, these can be different features, these question marks. These are the features we've chosen to split on. These can be the different features, or, as you know, again, from doing some of this in Data 610, this can be the same feature, but a different value of that feature. Maybe this was greater than $10,000, less than $10,000, greater than $10,000, and this was greater than $20,000, less than $20,000, so forth, okay? So we don't have to worry about that. Now, if you had to do figuring out the splits by hand, you would throw up your hand and say, it can't be done. Can't be done. Why is that? Well, I'm going to tell you why. Because here are the key questions. The decision tree key questions. I'm glad it wasn't 3 key questions, because I know it had decision tree 3 key questions. I wouldn't be able to say that. Decision tree key questions. First of all, how do we decide where to split? We recognize those splits are very useful, but how do we know where to split? How do we know which variable, which feature to split on? How do we evaluate each possible variable to find the best value to split on? That's really key, isn't it? When do we stop? Do we keep going? We'll talk about that in a minute, because there can be a significant problem with overfitting in decision trees. So we'll talk about that in a minute. We'll come back to that. How do we assess accuracy? Do we use the standard measures, or are there some other measures? What if we go too far in the splits? What if this ties back into this one? What if we do find that we do have overtraining or overfitting? What do? There are ways to avoid that. Many of those are built into SAS Enterprise Miner, which is great, and you'll realize the value of that more so at the end of next week. But we'll talk a little bit about that tonight. Okay, so let's get into something with real numbers now. Let's say we have 9 circles and 9 triangles all mixed together, and we'd like to split or separate them into more similar groupings. So again, we find a value, an input variable to split on, and let's say we find a pretty good one, and it gives us 4, 5, 6, 7. We're testing. Maybe there's 15 things that determine whether you're a circle or a triangle, and you know we start looking at those variables, because you have to look at each variable. Let me repeat that. You have to look at each variable, and you have to look at each value of each variable. Let me say that again. In order to figure out the best split criterion, you look at each possible input variable as a possible split. You look at each possible value of each input variable as a possible best split for that variable. And then you pick the best. Now think about a problem where you had thousands of inputs, and many of those continuous, which means they have many values. That would be overwhelming if you had to do that by hand. We're going to do one by hand, by the way, or at least piece of it by hand. It would just overwhelm you. You see, many people forget that these techniques have been around for a while. What's over here and 1 triangle, and it ends up with 2 circles over here and 8 triangles. We're considering this. I wonder if this would be a good thing to split on, whatever this criterion was. Again, we'll do a real problem in a minute, but well, what if this was? Is that a good split? Well, what we have to do is calculate how well that value of that variable splits the data. Looked like it did a good job, but that's just visual. How well does it do? We have a way of measuring that, okay? We have a measure of node purity. Splits that lead to higher purity are better candidates. What do we mean by purity? More circles, fewer triangles here. More triangles, fewer circles here. What if I had another criterion that gave me all the circles here and all the triangles here? It'd be better, wouldn't it? What if I had another one that gave me 5 circles and a bunch of triangles, and over here 4 circles and the rest of triangles? That was good, right? Intuitively, we know that. But we need to be able to calculate that, because we can't just sit there and intuitively try to guess at this. So we use something called a Gini score. It's one of the common methods. There are a couple, but this is the one I like the best. And of course, SAS Enterprise Miner does do this. Now, I have one message that says you've lost communication. Can everyone else still hear me, I hope? Let's check and see. Hello, can anyone hear me? Sometimes communication does go away. Oh, good. All right, well, then whoever that is that lost, you may have to log out and log back in or something. Good. Okay, good. Okay, so remember, it's recorded, the whole session. But anyway, okay, so what do these Gini scores mean? Okay, well, you'll see how we calculate in a second, but the lowest possible score is 0.5, which means the classes, the answers, are represented equally in the node. That's bad. A high Gini score is what you want. The highest possible score is 1, where all of the circles are in one square and all of the triangles are in the other. That'd be a perfect Gini score. That's good. And so here's the formula. The sum of the squares of the proportions of the classes in a node weighted by the number in each node. And again, that's the kind of double talk you see in all stat books, isn't it? It's not all that confusing if you go through it slowly, but we're going to do a little calculation here in a minute. Sum of the squares of the proportions. So we have to get the proportions. We're considering a split. Now, this is when you're considering a split, because you have to consider all of them, remember, all variables and all values of all variables. So we're considering one. So what do? We say, what if I made that split? I would get the sum of the squares of the proportions in the classes for each of the nodes, and then I would weight those by the number in each node. So let's go back to this one. We are considering some value of some variable that splits our data thusly. It puts 8 of the 9 circles over here with one triangle. It puts 8 of the 9 triangles over here with, 7 of the 9 circles with one triangle. It puts 8 of the 9 triangles over here with the other 2 circles. So how do we calculate the Gini for that? Well, first let's look at the Gini for node 1 when we started. What was the Gini? We already know that when they're equally represented, the answer should come out to be what? 0.5. Well, let's see if it does. First of all, what's the proportion of circles? 50%. What's the proportion of triangles? 50%. What do we do with that? Let me go back. We square that. Square the proportions and add them together. Okay? So if we square 0.5, we get 0.25. If we square the other 0.5, we've got to square both of them, we get 0.25. We add them together, we get 0.5, which we knew was the answer. Because remember, when you have equal representation of the outcomes, the Gini is 0.5. All right, so that's what we started with. Worst case possible, right? 50-50. Now, this split, which we are evaluating to see if it's the best one, how does it do? Well, let's calculate the Gini for it. Okay, in this square, we have 1, 2, 3, 4, 5, 6, 7 circles out of 8 total items. Let's go back to this. Squares are the proportions. So what's the proportion? 7/8, or 0.875 circles, and 1/8, or 125 triangles in node 2, right? What do we do with those proportions? We square them. So 0.875 squared is 0.7656. 0.125 squared is 0.0156. We add those together, and we've got 0.781. Okay? That's the Gini for node 2. How about the Gini for node 3? Well, we have 2 circles out of a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 circles out of 10, so 20% circles, 80% triangles. 0.2 is the proportion, or 0.2 is the decimal version of the proportion. Proportion is 20%. 20%, 80%. 0.2 squared is 0.04. 0.8 squared is 0.64. And that Gini, for that node, is 0.680. Ah, but there's one more step, isn't there? Sum of the squares of the proportions in each node. We did that. Weighted by the number in each node. Okay. How many are in this node? 3, 4, 5, 6, 7, 8. How many are in this node? 4, 5, 6, 7, 8, 9, 10. So there's 8 over here, 10 over here. So there's one more step. We have to do a weighted average of the two new nodes. Okay? So we take the 781 weighted by 8/18, which is 4/9, 0.444. We take the 680 weighted by 5/9, which is 0.556, slight rounding. And we get an overall Gini of 725 for this considered split. That's pretty good. Went from 0.5, which is the lowest you can be, to 0.725, headed towards 1, of course, if we could get there. Not sure we want to get there, but if we could, that would be the max. That was one possible feature. We don't even know what the features are here. That was one possible split on one possible feature. One possible value of one possible feature. So what if you had to do that for several thousand features and several hundred, if not more, values of many of those features? A lot of calculations. They're not hard calculations, but it takes some time, which is why it's nice to have something like SAS Enterprise Miner or most powerful software these days that does that before you can hardly get your finger off the enter key. But that's what it's doing behind the scenes. It's calculating the Gini index for each possible split. And then, of course, you don't have to pick the best one, but normally you do. Say, now let's split on that. And we'll do more of that when we get into SAS Enterprise Miner specifics in the walkthrough next week. Excuse me. So there's our problem. What if we were split? These were categorical. These were shapes, right? Either a circle or a triangle. What if we were doing numbers? What if we had 9 ones and 9 zeros? Numbers. Okay. What criterion do we use to separate? Well, we still have to come up with a measure of node purity. We still want the split that leads to higher purity. Those are better splits than the ones that don't. So we still go through the same procedure, except, of course, we're not going to calculate the Gini index. We're going to deal with variance. Low variance, most scores are close to the average. That's good. High variance, many scores are away from the average. That's bad. And then the formula for variance reduction is find the average value of the node for the split you're considering and compute the variance from the average value in that node. So let's go back to our little problem. With 9 ones and 9 zeros, the average, I think you'll agree, is 0.5. Okay? And each observation differs from the average. Remember, that's part of it. Find the average value of the node and compute the variance from the average value. So the average value is 0.5, and the difference for each of these things is 0.5. We want the average. And so the variance is 18, the number of items in there, times the average variance squared divided by the number of 0.25. That's the variance. We like to reduce that. Let's say we are considering a criterion that will split it. Okay? And here's how it would end up. We'd end up with 4, 5, 6, 7 ones and a 0 over here. We'd end up with 4, 5, 6, 7, 8 zeros and 2 ones over here. So what's the average value of node 2? Well, it's 7 times 1 plus 1 times 0 divided by 8, 0.875. What's the average value of node 3? 8 times 0 plus 2 times 1 divided by 10, 0.2. What's the variance across both nodes? Well, the ones differ from the average value by 0.125. So we take that variance for the ones and square it, multiply it by 7. The 0 differs from the average variance by 875. We square that, multiply it by 1. There's only 1 0 over here. And then we add those up, divide by the total, and get that, 0.138. And so the variance, well, that's for that side. And then this is for the right node 3. Okay, this is node 2, this is node 3. And then variance reduction is 0.25, which is what we started with, minus 138, which is what our new variance is, added across both nodes. And these two numbers are for the left node, node 3, or node 2. These two are for the right node. And the total is 18 cases. So we've reduced our variance from 0.25 to minus the variance we now have. We reduced it by 112. That would be compared against every other possible variable to split on and every other value. And by now you should say, Thank goodness the software does that. Okay, because that's very important. Obviously, it's a lot of calculations for a large problem. Not overwhelmingly complex calculations, but a lot. Somebody's got to do them, right? A lot of calculations. So let's look at another example. This is right out of a nice book. I like this little example. It's small. Again, you can't really do large examples by hand because you just be calculating and putting chart after chart after chart up. So you need to find something reasonably small. So I've liked this little example from Excel Miner, another software package, but it's a simple example. We have 24 households, some of whom own a riding mower, some of whom don't. Turns out 12 of them own a riding mower, 12 of them do not. Okay, this is just their household number, meaningless, of course. This is how much money the household makes in the income. This is the lot size of their yard in the blue column. Okay, so there's only two features. We're trying to predict whether a person owns a lawnmower or not. We've only got two features to pick from. Now, again, normally any kind of even a small, reasonable problem is going to have a lot more features. These happen to be both what we call continuous features, meaning they're not yes, no, circle, triangle. They're values, aren't they? Numbers, which can take on a lot of different values. So I thought this would be a good example to sort of show. Well, we have two features. So where we're going to start. Okay, the objective is to create a decision tree that classifies whether someone is a lawnmower owner or not. So that when someone comes in, we ask them a couple of questions, maybe about their income, maybe about their lot size. Not sure yet until we build the tree. And we say, you know, I think you own a riding lawnmower, or I don't think you own a riding lawnmower. Right now, we would be what? Guessing, because half the people in our data set from the past do own a riding mower, and half don't. And we don't seem to have any clear-cut thing here. And when you plot this, it makes it look a little bit more interesting, doesn't it? The non-owners, the red squares, tend to be lower income and have smaller lots to mow. It makes sense. Riding mowers aren't cheap, and you don't need a riding mower if you have a small amount of grass to mow, do you? Tend to be. But there's some weird things that happen, like here's somebody who has a riding mower who doesn't make a whole lot. And here's some people who make a lot more than that person does, but don't have a riding lawnmower. And here's some people who you would think, well, these people you would think way over here with a lot of income and a reasonably sized yard would have a riding mower, but they don't. And here's some people over here, maybe this person and so forth. But anyway, this is a very simple case still, but it's got a lot of stuff in it. So it's just a plot. And the reason I'm showing the plot is because sometimes the plots are insightful, and I'll show you in a minute why. So what's next? Well, remember what we said. We consider all possible splits. So we have to consider each variable. We have two, lot size and income. We have to consider all possible values of each variable. Now, when you have a continuous variable, what do you consider as a value? I mean, we have 24 different values for lot size. We have 24 different values for income, don't we? Each person has a little different value for each of those. Well, what we usually do is use the midpoint between pairs of consecutive values of the variable as the possible split. I'll show you what I mean. Here's our original set, sort of the way it came in, 1 through 24. We have to consider on splitting on income. We only have two things to consider. We can either split on income or lot size, right? Or lot size. And we have to consider splitting on every midpoint between two values. So what we need to do is put these things in some order so we can get those midpoints. Same thing for income. So let's say we take the income and forget the household number. We don't really care about that. Let's order it from lowest to highest. Lowest, 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 highest. So there's the lowest income case. 109.05 is the highest income case. So we will consider splitting on a value between these two. We will consider splitting on a value between these two, 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 dot, dot, dot. So yes, you have to do the calculations, that variance calculation for every one of those possible splits on income. Here are the lot sizes. We rank order those from smallest to largest. And yes, we would consider a split on the midpoint between 14.4 and 15.4, on the midpoint between 15.4 and 16.2, on the midpoint between 16.2 and 16.6, etc. So there's a lot of possible calculations. So you have to consider all possible splits, use each variable and all possible values, and then you rank all the splits on their contribution to homogeneity. Okay, just like we said, use the Gini index or some other measure, reduction in variance if it's continuous. Okay, which one reduces the entropy most? Okay, so let's go back and calculate our starting Gini index. Here it is, 0.5. And let's say somebody does all these calculations and it turns out the best first split is on lot size of 19. Now, I'm not showing the calculations because I didn't do them, but certainly you put this little data set into any software package, including SAS Enterprise Miner, it will give you all the Gini indexes, and it turns out the best one is the first one to split on a lot size of 19. So it's not on income, it's on a lot size of 19. Now, it wasn't a perfect split, was it? Because we didn't separate all the owners from the non-owners. We separated a lot of them. Above the green line, we have 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 owners and 3 non-owners. Below the green line, we have 4, 5, 6, 7, 8, 9 non-owners and 3 owners. Okay? So it did a pretty good job. And it turns out this is the best split you can do. So now if somebody comes in and says, I have a yard that is more than 19,000 square feet, we say, you know, I'll bet you own a riding mower. Would we be right all the time? No. No, because here's at least 3 cases where that wasn't true. If they came in and said, I have a smaller yard, it's less than, we'd ask them, is it more than 19,000 square feet? No, it's less than that. We'd say, I bet you don't have a riding mower. Would we be right all the time? No. But we'd be right more than if we just guessed based on our original set of data, which is 50-50. So that's our first split. Do we stop there? Well, maybe. I doubt it, but maybe. You know, say, no, see if I can do another split. Turns out, here's the calculations. We started with a Gini index of 0.5. After the split 1, we have 3 owners, 9 non-owners. So even though our variable is a continuous one that we split on, we're using the Gini index because our answer is categorical, either you're owner or non-owner. Okay, so we use the Gini calculations. So after we split, here are the calculations. We can go through those again. Remember, it's the proportion. So, okay, we have 12, and we have 3/12, or 1/4 owners, and 3/4 non-owners. So we square those, add them together, right? Over here, we have 9 owners, 3 non-owners. 9/12, 7.75 squared, 0.25 squared, add those together. Then what? We add these two together, weighted by how many are in here. Well, there's 12 in each, so it's going to be 0.625 times 0.5 plus 0.625 times 0.5, 0.625. So, excuse me. So our Gini index started at 0.5, a 50-50 guess. We now know that if you have a lot size less than 19, we're pretty confident that you don't have a riding mower. If you have a lot size greater than 19, we're pretty confident you do. What if we want to split again? We do the same thing. Now, I'm not going to show the calculations for the rest of these splits, but it works the same way. Because now we take a look, and by the way, now we're going to take a look at this node and figure out the best way to split it into 2. And we'll take a look at this node separately and figure out the best way to split it into 2. And they may be different criteria. Turns out the best way to split is the next thing is to split below the green line, the best way to split it, which would be the people making with less than 19,000 square feet. The best way to split them up is on income, okay, at 84.75. What does that do? Well, it gets all these characters over here to the right, and all but one of the squares is now over here, okay? So that's split, the second split. So we have 3 owners, non-owners. After split 2, which is 84.75, we end up with 1 owner and 9 non-owners. And over here, 2 owners and 0 non-owners. Okay? So we got all the non-owners in one spot. They're all over here. So if your lot is less than, well, we got all the non-owners that are below the green line over here. We do that split. Okay. So if you have less than 19,000 square feet and you make less than 8475, we're pretty sure you're a non-owner. Not positive, but pretty sure. If you have a lot size less than 19 and you make more than 8475, we are 100% confident, based on our data set, that you own a riding mower. There's only two of them, and they're both over here. And again, you can do the Gini calculations. We have 10 here, we have 2 here. So 1/10 squared plus 9/10 squared added together. Over here, 1 squared plus 0 squared, because that's 100%, gives you 1. We have to weight that by the number of things in each of these squares, remember. So it's 0.82 times, most of them are over here, 10 out of the 12. So 10 twelfths, or 5/6. So 0.82 times 5/6 plus 1.0 times 1/6 gives us 850. So we've raised the Gini index from 0.625 to 0.850 for this level. Now let's do the same thing going the other way, where the people who have more than 19,000 square feet. The best split for them was also on income, and it turns out it's at 5715. Same kinds of calculations. Again, going through these, even if they're trivial, sort of helps cement the concept, I think. If we split, this was the best split. I didn't do all the calc. Remember, there's dozens of calculations you'd have to do to check them all, but this is the best one. So less than 5715, $57,150. We end up with 1 owner and 2 non-owners. Greater than that, we end up with 8 owners, 1 non-owner. They're the Gini numbers. And so we've raised this Gini from 0.625 to 0.740. Okay? Now what do? Well, you could keep going, because we still don't have total homogeneity, do we? We still have 1 square over here, or 1 blue star, whatever that shape is, that we really shouldn't be over there, because everybody else is a non-owner. We have 1 down here that shouldn't be there, because everybody else is a non-owner. And we have 1 non-owner here who shouldn't be there, because everybody else is an owner. So if you said, I'm going to keep going until I get 100% homogeneity, well, there is a tree in the book until you can go. Now, when do you stop? Well, as I said, one idea would be, I'm going to go until I get purity. I get purity. I only have cells, leaves we call them, where everybody is the same, or everybody's an owner, everybody's a non-owner. That is likely to be overfitted. I'll say why in a little bit. So each leaf is pure. Or you could say, I'm going to stop splitting. Let's say you started with 10,000 cases. I'm going to stop splitting when a leaf only has 50 cases in it, because that's crazy. That's such a small sample, it doesn't mean much. Okay? In this case, we only started with 24, but, you have to stop somewhere. Or I can say I'm going to stop when the tree reaches 6 levels deep. SAS has a default of 6 levels, by the way. You can change that, but 6 levels deep. Why 6? Well, you're starting to get cutting the bologna pretty thin when you get down below 6 in many cases. But you can change that. Or I can stop if there's no significant splits. Now, what do we mean by significant? Well, you can do a chi-square test and see if the next split is going to be significant in terms of its reduction in the variance and the increase in homogeneity. So here's the complete split on all this thing. You can see it took quite a few splits to get to where we now have pure cells or pure leaves. Look, only 2 non-owners there, only 1 owner there, only non-owners here, only owners here, only non-owner here, only owner here, only non-owner there, only owner, only non-owner, only non-owners, only owners. So yeah, if you want to build a tree that deep, you will end up, but now you're getting down to where, gee, these are such isolated cases that you've likely overfit your data. Now, how do we know if you've overfit the data? I said likely. And the way we know is if we find out that, remember, we always have a test set and a training set. We did all this model building on what? The training set, which is usually the lion's share of the data, maybe 65 to 75% of the data we use to train it. That's how we get the splits. But we held out, let's say, 25 to 30% of the data and put that in a test set, or sometimes as SAS calls it, a validation set. What do we do with that? Well, once we have a decision tree that we think is good to go, we test it against the test set and compare. In this case, we probably compare the classification matrix, the confusion matrix, if you will, and see if it held up. You know, if it was overall accuracy with the training set was 88%, but it's only 60% with the test set, we got a problem. If it was 88% with the training set and 85 or 86% with the test set, we're probably okay. And again, there's some subjectivity in there. As I said, you don't want to have a tree so far down that it actually ends up, you could actually take it down to, let me go back a bit. I can continue to split this until each of these individual cases is by itself. I can say, all right, well, we got all these that are non-owners, but what if I want to get them I want to know about this non-owner. Well, I could split here and here and, keep going. You'd end up with a goofy looking set of rules, but it would say, if you weigh more than 168.6 but less than 170.1, and your income is more than 57.5 but less than 58.30, and your lot size is more than this and this and that and the other thing. Of course, weight's not in there. But you could go through and come up with a whole set of granularity that got it down to where each individual case was in a leaf by itself. Well, that would be ridiculous. And that's what happens if you go too far down. So when you get new observations come along, so somebody walks in and you want to determine whether they are a lawnmower owner or not, or you're thinking of mailing out to people an offer, a sale on lawnmowers, riding lawnmowers. Do you mail out to everybody that you can get in the mailing list of 100,000 people and it costs you $7-8 per person to mail out something nice, a brochure? No. You would sort through that, follow the rules, and put people into pots where you are more or less confident that they would like to buy a lawnmower based on the fact that past cases did in fact own a riding lawnmower. And then you would only mail to those people. So now we get into the lift concept, right? So when new cases come in the door, if it's a classification model, you filter them through the tree. At the terminal leaf, you say you are likely to buy a mower, not likely to buy a mower, likely to churn, not likely to churn. This is a fraudulent transaction, not fraudulent transaction. If it's a prediction thing where you're trying to predict how much money they could borrow, then of course you filter through, and at the terminal leaf, if you're whatever terminal leaf you're in, based on the rule set, you get the value of the leaf, because the leaf's going to have values in it that have to be averaged, the average numerical value of the training data in that leaf. So that's how you drop new cases through. We don't do any of that because we have test set, training set with SAS. We don't have unclassified sets, new customers walking in. So the next thing we need to discuss briefly, of course, is now that we have the decision tree, we turn it into rules. That's based on the path through the tree. Easy to operationalize, you remove redundancies. So here's a couple of rules. If lot size is greater than 19 and income is greater than 57.5 and lot size is greater than 19.8, then class equals owner. This is just showing part of the tree. There's the 19 split. You say, well, lot size is in there twice. That's a silly rule. And the answer is that's fine, because remember, there's several splits here on lot size. Several splits on lot size, 1 or 2 splits on income. If you turn that into a rule, remember the way rule-based systems work is once they have an answer to a question, they won't ask it again. So if they ask you, what's your lot size, and you say 20, it's going to say, that's true. And then they're going to ask you your income. And if you say 60,000, they're going to say, that's true. They're not going to ask this again because they already have stored in memory that your lot size is 20. So this would be true, this would be true, this would be true. Then they say you're an owner. And of course, if it's a new customer, you'd say this is someone I might want to mail a brochure to. If the lot size is less than 19, income is less than 84.75, and lot size is less than 18, then non-owner. Again, it would ask you this question: what's your lot size? And if you said 17, what's your income? 30,000. it's going to say, well, that's true and that's true, and I already know lot size, it's less than 18. It's not going to ask that again, no, and so forth. So the beauty is the redundancies would be eliminated. In other words, it looks like these are redundancies because it's got two, we only had two things to split on, so we had to keep splitting on finer and finer granularity of lot size and or income to get there. See, this one's lot size, income, and lot size, split on lot size 3 times. No. But remember, it's only going to ask once. You saw that again in Data 610 with the rules that came out of Big ML. So that was a good example. Okay, now we need to say a little bit more about overfitting. I've mentioned a couple things about it. When the model is basically fitting the noise, there's random variation. There's somebody who has a little teeny postage stamp yard but wants to have the prestige of having a big riding mower, and they buy one. Okay, that's more or less noise. Not really cause and effect. May not make sense, economic or physiological in terms of what you want to do, but there's noise, randomness out there. If you start trying to model the noise in any predictive model, you get into trouble. That's really when the overfitting shows up. You're modeling the noise, not the true relationships. Okay? Not always easy to detect that, but you're modeling the noise and not the relationships. So your data fit the model a little too well, at least on the training data. The way to detect it is with the test set. That's the holdout sample. And then there's a high probability that if you have overfitting, you're going to get some very bad results on the accuracy measures of your test set. With large data sets, with lots of predictors to choose from, there can be a lot of noise. A lot of noise. It could be from individual correlations, not the model. Basically, the noise is built into somebody doing something silly. So here's kind of conceptually what it looks like. First of all, we always have a training set and a test set. You always have to have that. The smaller the number in the nodes, the more danger of fitting only the training data. Remember I mentioned that. When you keep splitting, getting smaller and smaller number of cases in each leaf, you're running into some dangers there. So the danger is fitting the training, but not the test set. So if you keep splitting, it's going to keep fitting the training data better and better. The more splits you do, eventually you're going to get homogeneity, or down to where there's absolutely no two people who have the exact same lot size, exact same income. One has a mower and one doesn't. Well, you can't split that because you only had those two variables. But basically, you can almost always split down to where you get pure homogeneity. But the unseen data. So this is where you should have stopped splitting, right here. And in fact, you'll see when we do SAS Enterprise Miner, it tells you, it says you should have stopped splitting here, which is really nice. You have to do a little grasping of some of the concepts in there, but that's okay. So the tree is starting to model noise once you get past the minimum. This is the unseen data. This is the test data. Okay, you should have stopped here because there it's best on the test set. So how do I know where it's best on the test set? Well, I do the first split and go against the test set. I do the second split, go against the test set. I do the third split, I stop that, pretend it's a model, go against the test set. Fourth split, test set. Fifth split, test set. This is what SAS Enterprise Miner does for you. This is what the beauty of the software. It keeps sort of stopping at the end of each split, running it against the test set, and remembering how well it did. And as long as every time it does a split and does better against the test set, it keeps going. When it gets down here, it says, oh, we're doing good against the test set. And then when it does this split, it does worse against the test set. And that's when it says, oops, I should have stopped there. So, Mr. Model Builder, I'm going to tell you that you should have stopped here at split number 5. Isn't that neat? We'll do more of that next week. So you can set the rules to stop the growth of the tree. You don't have to wait for things to happen. You can limit the tree depth, as I said, the maximum number of the minimum number of observations that have to be in a leaf or a node, the minimum reduction in impurity. You can use these measures such as shade or the p-value of the chi-square test to see if the improvement is significant. In other words, yeah, it split and it got better, but was that a significant improvement? The chi-square test will tell you that. If you do overdo it and build a full-grown tree, there are ways to prune it back to a level where it isn't overfit. This they say is usually, and again, they're not talking about necessarily SAS Enterprise Miner because it does a pretty good job of telling you where to stop. But most software packages aren't going to do that. Okay? Most software packages are going to keep going unless you give it some of these depth things. But let's say you don't, and it goes all the way to the bottom, and now you find out, oh my God, I built a tree that's way overfit. What do? Well, you sort of back it up. You start going back and removing some of the splits, and those would be the branches, the splits that have the fewest observations. And you back it up, and then say, test that tree. Is that any better? Test that tree, test that tree. So you continue lopping off the weak branches, reducing the size of the tree until you sort of back into optimality. You'll see that SAS has some really good features to help you with that. But this is conceptually the way most software works. You go all the way to the bottom, and then you sort of back it up yourself. But of course, why not automate some of that, which some packages do, some packages don't. So you prune the full-grown tree back to a level where it isn't overfit. Okay, and these are a couple of methods used for that. We don't want to get into those tonight, but we can. You generate subtrees successively smaller, and then the best tree is the one that minimizes the error on the validation test set. If it's a classifying model, we use the misclassification rate. If it's a prediction model, in other words, numerical continuous, we use the average squared error. Okay. Let's finish up by saying, what are the pros and advantages and weaknesses of decision trees? Well, first of all, I mentioned many of the pros. No need to transform variables. It can handle all kinds. You don't have to worry about missing values. The variable selection, and remember, this is a biggie. Variable selection is a biggie when it comes to regression and neural nets, especially neural nets. Regression has a little bit of help, but neural nets, not much. Is automatic. And, of course, it can use numeric and discrete values, and it translates into parent rules. What are the cons? Well, you really need to have a pretty good data set, a large data set, to get a good tree with lots of possible split values and lots of possible split variables. And it may not be as accurate as other methods. Even when you get the best tree, there's no guarantee that will, and likely it will not outperform regression or a neural network model if there's a lot of nonlinearity in the data. Likely. Can't say always. Okay, so let's look ahead. What do you have to do for weeks 4 and 5? This being the start of week 4. And of course, by the end of week 5, you're going to be turning in your first assignment, your decision trees. So look ahead and start going through that SAS exercise. Part of that getting started with SAS Enterprise Miner 13.1 has a decision tree walkthrough that you can follow along and build a tree. You want to start looking at the options, trying some things. You want to start looking at Sarma, his explanation of the decision tree approach in SAS. You really want to start looking at some of those data sets and deciding if you want to use one of those or if you want to go out and try to deal with a real data set, real world data set. Again, there are some at UCI which are pretty good. They've been used for years and years, so they've been all the bad stuff has been squeezed out of them, so to speak. But they're not what I would consider real world data sets. They're in the same category as the data sets we get with SAS, maybe a little bit larger. So what are we going to do next week? Well, next week we're going to go through a little bit more SAS-specific kinds of decision tree approaches and some of the SARMA steps and talk about the SARMA approach. As always, if you come across interesting insights, tips, tricks, or even problems, there's plenty of room in the discussion area to contribute those insights, those experiences. I'm sure some of you, I know there's a couple of you that have a lot of experience with SAS Enterprise Miner, probably know some of the good tricks and tips, and feel free to post those because I don't claim to be the fount of all knowledge by any means. And of course, as always, you can ask questions at any time. So, as you know by now, this is the finale. This is the last slide each week. It says, if there's a question that you want to ask right now that the answer to which would benefit everyone, feel free. If I've been confusing or obtuse on something tonight, I'd like to try to clarify. If during the week something occurs to you, and again, the answer would benefit all, put it in the Let Me Have Any Questions discussion area or in one of the more specific ones if it's a specific item. And as always, anything personal or crisis-oriented, email and or call me. I see now a question in the chat room. Is random forest a part of this decision tree exercise? The answer is no. Random forest is an ensemble model. We'll cover a little bit of that in week 10, although at the current time, SAS Enterprise Miner does not do random forest. As soon as I said that, John Cook chiped in and says SAS Enterprise Miner doesn't do random forest. Well, I'm glad I said the right thing, John. I knew it didn't. Why, I don't know. I keep seeing hints that, yeah, it does the GBM. We're going to talk about ensembles. So for this exercise, don't get into the ensembles. Gradient boost, add a boost, those kinds of things. No, you're going to build just a couple. You're going to build 2 or 3 trees. I think I asked for 3. You're going to build 1 automatic, going to build a couple by hand or vice versa, and do some tricks with it and try some things, and then present your results as well as any insights you may have gained and so forth. But the random forest is a pretty neat way to approach decision trees. Remember, we did random forest in Data610 because the Big ML had that as a feature. That they may have added it. I think they probably had it when your cohort went through 610. They've added it within the last year and a half. So I think it was there. It's there now in Big ML. I think it was there then. And Big ML doesn't do all the things SAS Enterprise Miner does by any stretch of the imagination, but it does a really nice job on decision trees. Okay, good question. So no, we're not doing anything with any kind of ensemble yet. We're going to save that for week 10 when we deal with ensembles. Okay, I'm going to go ahead and stop sharing my screen, which is in my first step to get back to the real world. And now I'm going to go and stop the recorder.